Okay, so first thing is that this morning I went through these problems from the packet, page 5 and 6, 1 through 4, and I will put those. I'll put that recording up on my website under today's date. So if you wanted to check with any of those problems, I'll have that up. Yeah, hopefully by this afternoon. Okay. So in your packet, page 9, I want us to go through a couple of things today. There's 3 topics that are left to go over, and then we can start our review. The first is similar triangles. So we did similar triangles with cones, but then this is a similar triangles involving what we call the shadow problems. I think it's a little bit easier than cone problems. We don't have to create, or we don't have to do a lot of substitutions. Once we get the trick, our similar triangle ratio going, then that's the only thing that we need. We just have to understand what each of these variables represent. Okay, so give me 1 second here. All right, so let me read the problem and then talk about what this diagram means. Okay, so page 9. Okay, so a man is 6 feet tall, walking away from a lamppost at a rate of 5 feet per minute. So the person that's 6 feet tall is going to take this location of the triangle. We have a triangle within a triangle. The lamppost is 20 feet tall. Okay, and the light that comes from that lamppost is going to cause the shadow to be cast on the ground, and that shadow is going to be represented by Y. So we're going to create a triangle in this form, and I want to draw the triangle again so I can kind of show you all the different parts to it. But basically, we have this. We have we're going to create a similar triangle relationship between the 2 triangles, between the larger and the smaller triangle. So here in one color, I will represent the small triangle. In the large triangle, I'll put in a different color here. Okay, so let's do this here. Draw a triangle again here. So the height of the person is the height of the small triangle. The height of the lamppost is the height of the large triangle. And then we're going to let X and Y be part of the base. Okay. All right, so we're going to create proportions here. We're going to say the height of the small triangle is the height of the large triangle. So we'll say 6 over 20 as, okay, next is the base of the small triangle is to the base of the large triangle. So in this case, based off the variables that I have, what represents the base of the small triangle? Y, okay, Y, right? So Y divided by the base of the large triangle. What's the base of the large triangle? X plus Y, yeah, not X times Y, X plus Y, okay. All right, so the thing that's easier about this compared to cones is that this is the only equation that we're working with. We don't have to worry about finding a substitution, plugging into a different equation. This is the only equation that we're working with, okay? And now we're just going to cross multiply and just try to get this equation down to something that we can work with. Once we get everything cleaned up, we'll be able to find the derivative. So cross multiply, distribute the 6 through. Okay, so combine, distribute and combine like terms here. So I got 6x plus 6y. Subtract 6y from both sides. I get 6y equals, sorry, 6x equals 14y. So now that we have our equation as cleaned up as we can, we're going to take the derivative. Okay, so for data rates, every variable gets impacted by time. We have a relatively simple equation to find the derivative for. So let's go ahead and do that. So 6x becomes what?
60.
Good. Every variable is still impacted by time. So even though the x disappears, we still have that dx dt come up. Okay, 14y becomes 14 dy dt. Okay, so now let me talk about what these variables mean, because now it's a matter of plugging in and solving. Okay. Now, as the person is walking either towards or away from the lamppost, that's going to affect the x value. Okay, and as a person is walking, as the x is either increasing or decreasing, that's going to represent the rate that the person is walking in terms of that distance either increasing or decreasing between the person and the lamppost. Okay, so the rate of change of x is how fast this person is either walking towards or away from the lamppost. Okay. Next up is the rate of change of y, dy dt. Dy dt represents the rate of change of the shadow length. So as this person is walking towards or away from the lamppost, that's going to affect how long this shadow length is changing, right? So as he's walking towards the lamppost, his shadow length is going to decrease, okay? And as he's walking away from the lamppost, that shadow length is going to increase. Okay? So that's what dy dt means. And finally, the tip of the shadow. So the tip of the shadow is the shadow in relation to the ground. So as the person is, let's say, walking away from the lamppost, the speed that he's walking and the change in the length of the shadow is going to impact the speed of that tip. So tip of the shadow is going to move much faster than both the person and the length of the shadow increasing. So that tip of the shadow is going to be the two rates added together, dx dt plus dy dt. Okay. All right, so now that we see everything in front of us, let's go back to the problem and let's define some of these or assign some of these numbers to values. Okay, a man is 6 feet tall. We have that already. Walking away from the lamppost at a rate of 5 feet per minute. Okay, what can we assign 5 to? dx dt, positive or negative? Positive. So as he's walking away, this x is increasing over time. So we'll say dx dt equals 5. Okay, part A, how fast is the shadow growing? How fast is the shadow growing? Okay, so what is that referring to? dy dt. So change, rate of change of the length of the shadow. So dy dt is the unknown. When the person is 30 feet from the lamppost. That's x. Okay, so x is 30. Now, the way that these problems are designed, this 30, okay, well, first, let me ask you this. Can we solve for dy dt with what we have? Okay, so if we look at our equation here, right, it's a simple equation. The only thing that I need to solve for dy dt is dx dt. I do have it. If I insert 5 into dx dt, I'll get a number, and that number I can get to dy dt. Now the question is, does it matter what the x value is? The x is not factored into this equation. So it's almost there as a distractor. It's not, you see it in your homework, and it's just not part of the problem, which means that it doesn't matter if the person is 10 feet away, 3 feet away, 2 feet away. his rate is not going to change. Okay? The rate at which the person is walking and the length of the shadow changing is not going to be affected by how far he is away from the lamppost. Okay, so let's go ahead and find dy dt. Okay, we divide both sides by 14. And reduce this to be 15 over 7. So we know that dy dt, the rate at which the shadow is changing, the shadow length is changing, is 15, positive 15 over 7 feet per minute. As he's walking away from the lamppost, that shadow length is going to be increasing. Okay, so then part B, how fast is the tip of the shadow moving when the person is 30 feet from the lamppost? So how do we calculate the rate of the tip of the shadow? Yeah, we add the two rates, right? So we have dy dt, we have dx dt. Just add them together. Okay, so I'll represent ROC, rate of change of tip of the shadow. Dx dt plus dy dt. Five plus 15 over 7. Okay, so these problems are very specific. That's a very specific way of setting up, very specific definition of these variables. But once you've seen one, then you can kind of set them up for all these types of problems. Any questions? All right, so why don't we just try one on our own? Number 2, virtually the exact same setup. And you're just going to go through and see if you can practice through these steps and see if it all makes sense. I do want to point something out in terms of common mistakes. I see a lot of students do this when they set up their proportions. They will say x over x plus y. Now, why is it not x over x plus y?
X is
Okay, because does x represent the base of any full triangle? No. Right, it doesn't represent the base of any full triangle. So, I mean, unless we rearrange these variables, then we can do that. But if you rearrange the variables, then you're going to have to adjust what dx dt and dy dt mean. So I'm just going to keep it the way it is. If you want to adjust it, you can. But if you want to set it up the way that I have set up, then this top needs to be a y, not an x. All right, so try number 2. See if you're able to make sense of these steps as you try them. What do you notice about dx dt?
Negative.
Because he's walking towards, right? Walking towards, that's causing that x to decrease. Right, so that's the main difference between this and the previous problem. Your dx dt is negative, which is essentially going to force all your other answers to be negative as well. The shadow length is decreasing, and then your tip of the shadow is also decreasing as it's heading towards the lamppost. So you set your proportions as small height is to the big height, 5/15, as the small base is to the big base, y over x plus y. Cross multiply, distribute, by terms. You can reduce if you like, but you don't have to. I made it all the way down to 2y equals x. Take the derivative, 2y becomes 2 dy dt. X becomes 1 dx dt. Solve for dy dt to get -5/2. That's part B. Part B is asking for the rate of change of the length of the shadow. And then part A is where the tip of the shadow, so you're going to add the two rates together. You'll take your rate of change of the length of shadow, the rate that the person is walking towards the lamppost, and we add those rates together, -7.5. Any questions with this process or procedure? Okay, so two minor topics to finish off this unit is from 8.7, and that is going to be on page 11. Halfway down, and it's going to be the two remaining topics are linear approximation and L'Hopital's rule. So linear approximation is really just getting to the tangent line equation. That's really, and then doing one little thing after we get to the tangent line equation. And L'Hopital's rule has to do with limits. Okay, we got through limits, but I talked about how there's one little thing we got to come back to and revisit with limits, and that is evaluating limits, but then using derivatives to help us give us another pathway to finding limits. Okay, so we didn't do this in unit 1 because we haven't learned about derivatives yet, but now that we know about derivatives, we can go back and kind of fill in and finish off that our unit with limits. Okay, so halfway down here on page 11, linear approximation. Okay, so linear approximation, it sounds complicated, but all it's doing is we're creating a line and we're using the line to approximate a point on the graph. Okay, approximating nearby y values on the graph using the tangent line equation. Okay, so here's the concept behind it. Let's say I had a curve, and let's say that curve was f of x. And let's say we're targeting this x value at 4. Okay. That point has some y value to it. If I plugged in 4 into the function, it will give me a y value. Okay. But we're going to create a second equation. And that second equation is going to be a line. Okay. And with that line, we're going to use the point and the slope from the derivative to create our tangent line equation. Okay, so once you create your tangent line equation, it may look something like this. Okay, it skims the surface of the graph at that point, and let me call it L of x. So let's say I were to plug in a value that is really close to 4 on the graph. And let's say I want to find f of 4.2. And let's say f of 4.2 is somewhere here. Now, let's say I wanted to approximate f of 4.2 using the linear graph. And let's say that point is over here. So the question is the line going to give me the same value as the graph? No, okay. So we call it an approximation. But is it going to be pretty close? Probably, because we're close to the source, right? But what if I wanted to do f of 10 versus L of 10? Right, the further I am away, the harder it is for us to say that it's a good approximation. So linear approximation is only good if we're close to the source of tangency, right? As soon as we get past that point, then a lot of things can happen, and the graphs are going to probably diverge, and it's going to be very different. But if we're talking about the tangent line at 4, then pretty much, right? Obviously, if we got even closer, like 4.1 or 4.001, then our approximation will be even better, right? But if we're relatively close, we're going to get a relatively okay approximation. So that's all we're doing here. We're not trying to decide how accurate the approximation is. That's more of a BC topic. We just want to be able to create this tangent line and just find an approximation, whatever that approximation is, okay, using the line. Okay. So I just want to kind of show you that you know how to do most of this. We're just going to do a final thing, and even that final thing, you're just plugging in that decimal. So, but the setup just takes a little bit of time. But once you get past it, you're going to feel like this is something familiar, because we've done this multiple times ever since. Every time we learn a new derivative rule, I'm always saying find the tangent line equation. Okay, so it says use linearization. That just means linear approximation to approximate the square root of 9.2. So the way you're going to set this up is you're going to create an equation, and you're going to just replace the decimal here is written kind of like in a strange way. Just replace that decimal with an x. That's all you're going to do, and that is the equation that you're going to create. That you're going to start with. Okay, y equals square root of x. That's the curve. Okay. And the next thing is you want to find a point. Now, to find a point, we want to use a nice point. We want to choose a point that is closest whole number that we can find to that decimal. Okay, what's the closest whole number? 9. Okay, so we'll plug 9 in. Again, ignore the square root. We're just looking at that numeric value. Okay. Okay, so with that point and the function, so now we're going to just cover that up. We're not going to use this for a while. We're just going to focus on just this information here. Now, how can I find the y value? Yeah, plug into the function, right? What's square root of 9? 3. Okay, so that's my point. Okay, next step, I'm going to find the derivative, and from the derivative, I can find the slope. And I'm just doing everything based off of this here. Okay, so to find the derivative, I'm going to get it ready. So how can I get it ready? Write this as x to the 1/2. Okay, find the derivative. So negative 1/2. Okay, good. Get it cleaned up. Now I want to find the slope. So to find the slope, I'm just going to take my derivative. I'm going to insert what? Insert the x. Yep, y prime of 9. That's my slope. Do some cleanup. What's the square root of 9? 3. Yep, 3 times 2 is 6. So 1/6. That's my slope. Okay, take your point, take your slope, and you're going to create your tangent line equation, much like something that this would look like. Okay, so tangent line equation: y minus y sub 1 equals m times x minus x sub 1. Plug in your point, plug in your slope. We know how to do this. We've done this many times. Okay. Nothing new so far. I mean, except for helping us interpret the starting point and getting it to the equation and the point. But after we found the function and the point, then everything feels the same, right? We've done this many times. Okay. So we've done the linear portion of our of this concept. Okay. But now we're gonna move on to the approximation portion. So I'm just gonna just do some rearranging. I just want to get that y by itself. I'm not gonna worry about cleaning up. I just want to just get that get that y by itself. No need to do any reducing or simplifying. Okay. Now the only thing left is the approximation, and this is where we're going to bring in the what? Yeah, bring in that 9.2. Now don't worry about anything around that 9.2. Don't worry about the square roots. If it's part of a fraction, we just want the decimal, and we only want the decimal. So now all we do is we just plug that decimal in. That's it. That's all linear approximation is. It just means find the tangent line equation. That's something that you already know. And then just insert the decimal that they give you. Okay, plug in the calculator. Okay, we know that this is not going to be the exact value of the original function, but it's pretty close because we're close to the point of tangency. Okay, it's a relatively minor topic, but it is something that we need to know for the AP exam. Okay. Any questions there? Okay, so let me see if I can walk you or help you get started with another problem on the back, just to kind of make sure that you're comfortable with this. And then I'm going to have you finish it. Okay, so on page 12, going to do another linear approximation with what's given. Are we okay with this page? Okay, use linearization to approximate cube root of -8.1. Remove the decimal and just put an x in its place and back to our starting function. Okay, find the closest whole number. What's the closest x value? Yep, -8. And then from here, just do all your work just from that information alone. Ignore the cube roots of the decimal. From here, you should be able to find the derivative, find the order pair, find the slope, point slope form. And then at the very, very end, you're going to finally plug in that -8.1. We'll see if you can work through that. Set it up for power rule, find the derivative, clean it up, plug in the x value, find the slope. Here's the process halfway through. Plug a -8 into the original function. That'll get us our y value. rewrite the cube root of x as x to the 1/3. Power rule. Get to the derivative, clean up. Now, how can I find the slope? Yeah, plug in the -8. Again, you're not going to do anything with the decimal yet. You're going to get everything built and ready just from this information alone. Okay, plug in -8 into x. Use your calculator, find your slope. Your slope will end up being 1/12. So you have your point, you have your slope, point slope form. Okay, so there's our equation. We just do a little bit of rearranging here. Just move that 2 over to the other side, get that y by itself. Now I've done the linear portion of it. What's my last step? Plug in -8.1. Again, don't worry about the cube root. You're just putting in the decimal number. Whatever the calculator gives you, that's your approximation. I just want to convince you that you already know how to do it. We're just kind of giving a name for this process. Okay. Tangent equation, plug in a decimal, we call that linear approximation. Okay. Any questions? Okay, so the final topic is L'Hopital's rule. So L'Hopital's rule allows us to find a limit using calculus or using derivative procedures. Okay. So we're kind of going back to unit 1 a little bit just for just to talk about this L'Hopital's rule. Okay, does anybody still need this? Okay, so let's review limits. Okay, with limits, I always say if it's approaching a real number, just go ahead and plug in that x value, right? We want to know what's happening. Is it a real number? Is there a hole? Is there a vertical asymptote? We want to know what's going on. So we talked about how if I inserted a value into a real number into the expression, and if I got 0 over 0, what does that tell us? There's a hole, but there's a, what is there? Is there a limit waiting for us?
Yes.
There is. We just have to kind of go through some algebraic steps, right? And that could be factoring, reducing. It could be conjugate method, finding a common variable, reducing, or complex fraction where you got to clean everything up, but you're still reducing and trying to cancel things out. So here, we're doing something a little bit different. We could do that, but this is called L'Hopital's rule, where once we get that 0 over 0 and realize there's no answer waiting for us, instead of going through the algebraic steps, we're going to take this very specific step of rewriting and creating a different version of the expression before reevaluating. So what we're going to do is we're going to find the derivative of the numerator portion, and then separately, we're going to find the derivative of the denominator portion. Now, I don't want us to think that this is some sort of a quotient rule. Okay, so quotient rule, if I want to find the derivative of this function, if I want to create a slope formula of f of x over g of x, then I will have to go through quotient rule. But this f prime over g prime is really just a workaround using derivative procedures to find the limit. So it's got a different purpose. So it's not anything related to quotient rule. So what we do is if we get 0 over 0, we realize there's a hole, but there's a limit waiting for us. We find the derivative of the top, we find the derivative of the bottom. That will give us a different version of the same problem. And then we reevaluate the limit, and that will get us down to a number, and that number will be the true limit of that function. So rather than going through a conjugate method, reducing, simplifying, we can just quickly find the derivatives of the top and bottom, and then reevaluate. Okay. So once you learn this is going to be for a lot of students the preferred method of doing limit problems, because it's almost like a one-stop shop, because it doesn't matter what the function looks like, as long as you get 0/0. Sometimes it's just faster to just find the derivatives and then reevaluate rather than going through and learning all those different algebraic procedures. But the reason that we did that at the beginning was to learn and to practice those methods, but also because we haven't learned derivatives yet. Okay, so let's go through the process and see what we have. So we never want to assume that we have a result before we actually evaluate it. So first thing we see a real number. Let's plug in. We always do that regardless of whatever you want to do. So insert 0 in for x, and what do we get? Square root of 1 is 1, 1 minus 1 is 0, denominator 0. Okay, so that confirms it. We have 0/0, and we know that we have this option of L'Hopital's rule because we have 0/0. Okay, so I'm going to write that limit notation again. I'm going to get my numerator set up for power rule, or in this case, chain rule. Get that square root rewritten. And I'm going to find the derivative of the top. Again, this is not quotient rule. We're not going to do this f prime g minus f g prime. This is really just for limits, for a workaround with limits. Okay, so chain rule says outside's derivative, so parentheses to the 1/2. Got the outside, and you got the inside, which is x plus 1. Okay, and we're going to take turns with each derivative, right? So what's parentheses 1/2's derivative? 1/2 parentheses to the negative 1/2. What stays inside? The x plus 1 times, what's the inside's derivative? 1. Okay, so we found the derivative of the top. And now we're going to do the derivative of the bottom. Okay, so x's derivative is 1. Okay, so we found the derivative of the top and bottom. The whole purpose of this is to create a different version that will hopefully give us something other than 0/0. Okay, so now we're going to reevaluate. Plug in 0. Remember, our goal is to still try to get the limit, so we don't want to leave our answer unfinished. We're still trying to get down to a real number here. So insert 0 in for x. Okay. All right, so 0 plus 1 is 1. 1 to anything is what? It's still 1, right? Doesn't matter if it's raised to the 1/2, it's still 1. And 1 times 1/2 is 1/2. 1/2 divided by 1 is 1/2. So that's our limit. So it's a very useful tool, but a couple of pitfalls that I want to point out is we can't jump into L'Hopital's rule without confirming of 0/0. So unless you get 0/0, we don't have the green light to do L'Hopital's rule. Okay, we got to get that confirmation before we do L'Hopital's rule. And the second thing, which I'm not going to take off points for, but just to kind of let you know, College Board is picky about equal signs. If you put an equal sign on the free response question, they're going to take that very literally. So if you see that equal sign, they're going to actually look at both sides of the equal sign, and they're going to say, okay, is it really equal to each other? Okay, if it's not, then points may be taken off. So a lot of times we don't use equal signs that way, right? We use equal sign as a way of saying, okay, this is my next step, but we don't necessarily mean that it's the same. So the way around it is we tell students to use arrows. If you use arrows, such a minor thing, right? But if you use arrows, then they understand, okay, you just mean for us that you want us to progress to the next step, but you're not necessarily saying that they're equal to each other. So L'Hopital's rule, the cleanest way to work through it, if you want to show your work, is just to use arrows along the way. Okay. Yeah.
How do you get to 1/2?
Okay, how to get to 1/2. So once I have my expressions, my other version through derivatives, I'm just going to plug in the remaining x's with 0. So if I plug in 0 in for x, 0 plus 1 is 1. 1 to the negative 1/2 is still 1. And then 1 times 1/2 is 1/2.
Thank you.
Okay. And even this step right here, right? You don't want to say equals 0 over 0. You want to say arrow 0 over 0. Now, I'm not going to take out points for that, but just to let you know what College Board expects. Okay, example 5. Okay, first things first. We don't want to assume anything. What's the first thing we should do? Plug in 2. Right? And what do we get? Okay, 0 over 4, what is that? That's 0. Is that a real number? Yes, so there's nothing more to do. Okay, we don't want to go through L'Hopital's rule if our answer is already there, right? Because if you try to go to L'Hopital's rule, you may come to 4/3, but that's not the limit because you haven't met the condition, right? We don't want to go to L'Hopital's rule unless we know that there's a hole and then we're trying to resolve that hole. Okay, example 6 looks a little messy. But the first thing we do is we plug in what? 2. Now, I'm going to speed this process up. Okay, I'm going to say that if you do plug this in, you are going to get 0 over 0. Which means we can do what? Go through L'Hopital's rule. Now, this is definitely a problem that you would prefer to go through L'Hopital's rule because you don't want to spend time trying to factor this, right? But derivative will go faster. Okay, so numerator, what's the derivative here? Power rule, we get 210x minus 420. And then the 420 constant goes away to 0. Okay. The denominator, apply that same process. Derivative is 216x minus 432. Okay, so we use our calculator. And tell me what you get. Zero over 0. So there's still a hole. That hole has still not been resolved. So guess what we can do? Yeah, that's right. We can find the derivative again using L'Hopital's rule. Okay. So this is the thing that we can do is every time we get 0 over 0, we get the green light to do L'Hopital's rule once. Okay. And if we reevaluate and if we still get 0 over 0, then we get another green light to do it once. Okay. But we want to be careful because we don't want to just keep blindly taking the derivative without first checking that we are getting that 0 over 0. Okay. So just make sure that you're always doing this 1 for 1, right? If you get 0 over 0, L'Hopital's rule once. Evaluate. If you get a real number, you stop. If you still get 0 over 0, do L'Hopital's rule again. Okay, so what's 210x's derivative? 210. The 420 goes away to 0. 216x's derivative is 216. So there we go. We have our constant. No matter what we do to plug in, we're still going to get that constant. Use your calculator. It'll reduce to a number. That's a real number. So we can stop. Okay. Now your homework is just going to come from the textbook. So 8.7 is the very last page of your homework sheet. You guys have mostly 2.6. There's also 8.7 in there. Don't worry about the linear approximation worksheet. You're just going to do the homework from 8.7. Next is L'Hopital's rule.
Okay, this is your first year teaching a shortcut with that you taught yesterday or the day before?
Oh, you mean L'Hopital's rule? Or which one?
One that you use, like, where you just take the derivative from
Oh no, yeah, we can only do this. Oh yeah.
Can I do it here?
Yes, he can do it. You could, yeah. But you can only do it if you already found a piece of this. Okay.
Did you last year then?
Okay.
Okay.
Okay. Or, Morgan, if I taught it, I may not have put it in the video, so is that what you're asking?
One of my friends was watching me do my homework and kind
Oh.
of helping me, and they like.
Oh, okay, got it. Okay, sorry, which one?
In your approximation.
I see.
She'll make it so difficult.